Hello. So far, we have used the central problem of understanding zeros of polynomials as our point of reference in exploring algebra. And what we've showed is that if alpha is a zero of a polynomial in a field extension, then what can we say about the ring after we join alpha to F? We showed that it's a field. We showed that it is isomorphic to a certain quotient of the ring of polynomials with coefficients inside F, and we described elements of F bracket alpha. Now, what we want to understand next is that for a given polynomial, can we actually find a field extension that has a zero of this polynomial? Next, we want to understand if there is a field extension that contains all the zeros of such polynomial. Is such a field a unique one, a canonical one? Can we talk about the smallest such field? So these are the questions that we want to address next. And we start with answering the first question, meaning we start by answering that there exists a field extension that contains all the zeros of this polynomial, and we make it small enough so that it is generated by the base field f and these roots, these zeros of this polynomial. So in some sense, we are going to give a smallest field with the property that all the zeros of this polynomial belongs to this field. We have to prove later that this is in fact in certain sense, smallest field that contains all the zeros of F. Of course, we can change the names and so on. That means the best thing that we can hope for is the uniqueness up to an isomorphism. So this is our goal in today's lecture and the next lecture. In today's lecture, we start with the existence and we show, we work towards the uniqueness, but we don't quite get there. Okay, but let's see what is the statement. So again, the statement is that we are given a polynomial which is not constant with coefficients inside a field. So capital F is a field. In that case, we want to show existence of a field extension, let's say field extension of field extension E of F, and elements alpha 1, alpha 2, alpha n inside this field extension, such that, first of all, my polynomial f can be written as product of these degree 1 factors, and because I'm not assuming that f is a monic binomial, I need to also multiply the whole product of these linear factors by the leading coefficient of the polynomial f. So first of all, I can decompose f completely into linear factors over this larger field. And second, this larger field itself is generated by f and these roots alpha i's. So there are two different ways of thinking about, or maybe multiple ways, at least two different ways of thinking about this ring f bracket alpha 1 alpha n. One way is saying that I'm adding these alpha i's one after another. So this was the smallest ring that contains f and alpha 1. Then I'm adding alpha 2 to this. So this would be the smallest ring that contains f, alpha 1, and alpha 2, and so on. So this is one way of defining this notation. An alternative way is by saying that, by describing all the elements of such a ring and saying that this is indeed the image of evaluation map when I evaluate a multivariable polynomial with n variables at the points alpha 1 alpha n. So alternatively, I can say that this consists of elements that are of the form some multi-index c sub I, then alpha 1 to power I1, alpha 2 to power I2, and alpha n to power in. So again, I'm evaluating a multivariable polynomial with coefficients inside f at the point alpha 1 to the dot alpha n. These are two alternative ways of thinking about this ring. But after all, what we are saying is that this is the field, this is the smallest subfield that contains f and alpha i's. So if I joined alpha i's to f, then these guys generate this ring, and that's another way of thinking about this ring. So again, what we want to show is that whenever I give you a non-constant polynomial f, we can find a field extension E of f that contains all the zeros of the polynomial f. So using the generalized factor theorem, we can factor out the polynomial f into linear factors. And because f is not necessarily monic, I need to multiply these linear factors by the leading coefficient of f. And this field extension E is generated by f and these zeros, alpha i's. So that is what we want to show. And here we are only concerned about existence of such field extension, and such a field extension we call this a splitting field of this polynomial. So I mean, the reason that we call it a splitting field is because we can split out, we can factor completely the polynomial f into degree 1 factors. We can split it, and that's why we call it a splitting field. So such a field is called the splitting field of this polynomial over f, and we want to show the existence. Okay, so how do we do it? So again, we want to factor f into linear factors completely. So what we do, we start with one factor at a time. And remember, we already know that f bracket x is a unique factorization domain. So that means we already know that I can factor f into irreducible factors. So this is kind of how we want to proceed. So again, what we do, we start with this f, we write it as product of irreducible factors, let's say f sub i's, and f sub i's are irreducible over f. Now, if I can show this result that we have over here for irreducible polynomials, if I can find some field extension over which these irreducible factors can be written as product of degree 1 factors, then as a result, we can write down f as a product of irreducible factors. So that means it's not surprising that we should start focusing on irreducible polynomials. So that would be our first step. And instead of factoring it completely into degree 1 factors, we are going to find a single degree 1 factor after a field extension. So that would be our first lemma. So again, what is the statement? Suppose f is a field, and I give you an irreducible polynomial with coefficients inside f. So here it's irreducible. Now, under this assumption, we are going to look for a field extension E and an element inside this field such that, first of all, f of alpha is 0, and second, E as a ring is generated by f and alpha. So E is f bracket alpha, and f of alpha equals to 0. So we are seeking a field extension E of f such that E is generated by alpha, where alpha is a 0 of the polynomial f. So remember, if we have such a thing, if E is f bracket alpha, we have already proved that in that case, in that scenario, we have that. So let's recall that if this was correct, then we know that f bracket alpha, which is our E, is isomorphic to f bracket x modeled by the minimal polynomial. And notice that f is irreducible and alpha is 0 of f. So if I if I divide out by the leading coefficient, that's precisely the minimal polynomial of alpha over f. So what I'm saying is that this f bracket alpha should be isomorphic to f bracket x modeled by the ideal generated by f. And remember, this isomorphism comes from the isomorphism theorem and the evaluation map. So essentially, this means I'm picking a coset representative, evaluate it at alpha, and I get my, my value in f bracket alpha. So in particular, alpha itself is the evaluation of the coset represented by x. So this means x, the coset represented by x, should be a 0 of my f, should be my alpha. So that's kind of a reverse engineering of the proof. So that's why we start with the ring, the quotient ring, f bracket x modeled by the ideal generated by f. And our claim is that we are going to show that such a E satisfies the desired properties. So that means E, we have to show that such a E is a field. It's a field extension of f, and it contains a 0 of the polynomial f. So let's start the proof. The first thing that we observe is that because f is a field, f bracket x is a PID. And now because the polynomial f, small f, is irreducible inside this PID, the ideal generated by f is maximal. So in general, the ideal generated by an irreducible element is maximal among proper principal ideals. In a PID, every ideal is principal, and therefore an ideal generated by an irreducible element in a PID is a maximal ideal. But we know an ideal is maximal precisely when the quotient ring is a field. So knowing that the ideal generated by f is maximal is equivalent to saying that the quotient ring of the ring of polynomials modeled by the ideal generated by f is a field. But that is exactly E. So we showed that E is indeed a field. Next, we argue that E is a field extension of the field f that we started with. So that means what? That means we need to produce an injective ring homomorphism from the field f into the field E. So we need to find an injective ring homomorphism from f into E. Okay, so what is my injective ring homomorphism? We more or less have only one good candidate. So f can be embedded into the ring of polynomials by viewing every element of f as a constant polynomial, and then we can pass to the quotient ring. So that means altogether, starting with an element C inside the field, I can send it to the coset represented by C. So that gives me automatically a ring homomorphism from f into E. Again, it goes through these that we are sending f to the set of constant polynomials. So that's an injective ring homomorphism. And then we are sending a ring of polynomials into the quotient ring. So the I that we are given here is in fact composite of two ring homomorphisms. In particular, this I itself is a ring homomorphism. Now, the next thing that we observe is that For instance, one identity of f is mapped to identity of E. So this is not the zero map. That means the kernel cannot be the entire f, but f is a field. A field has only two ideals. It's either zero or the entire field. And that means the kernel of I is a non-zero ideal of the field f, which implies that it is the zero ideal, which means the kernel is indeed trivial, and therefore I is an injective ring homomorphism. Alternatively, I can say that if C belongs to the kernel of I precisely when the coset represented by C is the zero coset. And that is equivalent to say that C belongs to the ideal generated by F. But remember, the ideal generated by F is a maximal ideal, and therefore it's a proper ideal. And a proper ideal can never have a unit. So that means this ideal, this principal ideal, cannot have a non-zero constant binomial. So the only constant binomial inside this ideal is the zero binomial, which means if C belongs to the kernel, it should be zero. So that implies that kernel is the zero ideal, and that means I is injective, which means we have a copy of F inside the field E. So E is indeed a field extension of the field F. So far we argued that E is a field extension. Now I want to show that it has a zero of F. Again, we borrow the intuition that we have from this backward engineering kind of argument, that if indeed it is F bracket alpha, then the zero should come from the coset that's represented by X. Okay, so that means I'm going to define alpha to be the coset represented by X, and then I'm going to check that it is indeed a zero of F. But what does that mean, that it is a zero of F? This means we need to evaluate F at alpha. In order to evaluate F at alpha, I need to have the coefficients of F inside the field E. A priori, coefficients of F are inside the field F, not inside E. This means I need to interpret, I need to view F as I need to work with a copy of F inside the field E. So to make it concrete, suppose that the binomial F is given by coefficients a sub n, a sub 2, a sub 0. I mean, a sub n minus 1, a sub 0. So these coefficients belong to the field F. Now, in order to work with elements inside E, I need to view these coefficients as elements inside E. This means I need to work with a copy of F inside E, and the copy comes from the injective ring homomorphism I. So that means F of alpha is nothing but I of the leading coefficient times alpha to the n plus I of a sub n minus 1 times alpha to power n minus 1, and so on. So that is F of alpha. That is the thing that I need to show is 0. But what is I of a sub j? I of a sub j is the coset that's represented by a sub j. So I of a sub j is the coset that's represented by a sub j. Now, what is alpha? Alpha is the coset that's represented by x. That means F of alpha is this quantity. It's the coset represented by a sub n times the coset represented by x raised to power n plus the coset represented by a sub n minus 1 times the coset represented by x raised to power n minus 1, and so on. But remember, in a quotient ring, all the computations are done with respect to the coset representatives. This means I have to pick these coset representatives, do multiplications and additions, and then consider the coset that's represented by this resulting binomial. So the resulting polynomial that we get out of multiplying a sub n by x to the n plus a sub n minus 1 by x to the power n minus 1 is this one. So we get that this is precisely the coset that's represented by this polynomial. This polynomial is nothing but the polynomial f. So we are getting the coset that's represented by the polynomial f. But remember, the ideal I is generated by the polynomial f. That means this polynomial does belong to this ideal I, which means the coset represented by f is the zero coset. And zero coset is precisely the zero of this field E. So altogether, we have deduced that when I evaluate f at alpha, I end up getting 0, which means alpha is a 0 of f. So altogether, we found this field extension E of f and an element alpha inside E that is a 0 of f. The last thing that I need to show is that E is indeed f bracket alpha, which means I need to show that every element of E can be written as in terms of a polynomial evaluated at alpha. But I mean, that is exactly the case because every element of E is represented by some polynomial. And that means that it is the polynomial with coefficients C sub j, I mean the coset represented by C sub j, which means the copy of f inside E. So we are taking a polynomial with coefficients inside f, but here we have to view f as a subfield of E, and then I'm evaluating it at alpha because x plus I is alpha, is precisely alpha. This is how we defined alpha. So altogether, I'm getting that every element of E is of this form. Some polynomial with coefficients inside f evaluated at alpha. And that's exactly f bracket alpha. So altogether, I'm deducing that E is nothing but f bracket alpha. And that's exactly what we wanted to show, and that finishes proof of this statement that whenever I give you an irreducible element, irreducible polynomial inside some ring of polynomials with coefficients inside a field, we can find a field extension that contains a 0 of this polynomial, and it is generated by this 0. Okay, so now we have this statement, but how can this help us to show existence of a splitting field? Again, what does that mean? We are given a field, we are given a non-zero, non-constant polynomial, small f, with coefficients inside this field, and we are seeking a field extension of f and elements alpha 1 dot alpha n inside this field with the following properties. So first of all, these alpha i's are all the zeros of this polynomial. So I can write down f as a linear product of as a product of these linear factors, possibly with the leading coefficient a, because these polynomials are monic, but f itself is not necessarily monic, so I need to multiply this product by this leading coefficient. And second, E is generated by f and the zeros alpha i's. Again, this is in the same sense as before. Either I can think about it like adding alpha i's one after another to the base field f, or I can think about it like a polynomial with n variables evaluated at values alpha 1 to alpha n. So both points of view work, that's fine, but this is what we wanted to show. And the way that we are going to show this is by induction, by strong induction on the degree of the given polynomial. So let's start with the base of induction. That means I'm dealing with a degree 1 polynomial, which means my polynomial is of the form ax plus b. In this case, I can easily factor out my leading coefficient. Notice that because it's of degree 1, a is non-zero, therefore it is invertible. It is inside, it's a unit inside f because f is a field, and therefore I can write it like this. And if I let alpha to be minus b over a, that's an element inside the field f. So this means the polynomial f itself has a 0 inside the field f, and I can take e to be f and let alpha to be negative b over a as above. And we see that this pair satisfies all the claims. First of all, E is precisely the ring generated by f and alpha, because that's precisely f. And the polynomial f is its leading coefficient times x minus alpha. So we get the result when the degree of f is 1. Now I'm going to focus on the strong induction step, and we are going to split it into two parts. Either the polynomial f is not irreducible, or it is irreducible. Okay, let's start with the case when it is not irreducible. What does that mean? This means, because capital F is a field, this is equivalent to say that this polynomial can be written as a product of non-constant or smaller degree polynomials. So I can find two polynomials, g and h, with coefficients inside the field f, such that the polynomial small f can be written as the product of g and h. So both of them have smaller degree and both of them are non-constant. So that's out of the assumption that f is not irreducible. But now I can use the strong induction hypothesis. Notice that degree of g is strictly less than degree of f, and the coefficients of g belong to the field f. So I can find some field extension and split g completely and write g factor g as product of degree 1 factors. So again, by the strong induction hypothesis, I can find a field extension, let's call it E1 for now, and elements alpha 1, alpha 2, alpha m inside this field E1 with the following properties. First of all, G can be written as product of these degree 1 factors, x minus alpha 1, x minus alpha 2, and so on. And possibly I need to multiply it by a leading coefficient of G. Notice that in this decomposition, I'm not claiming that alpha i's are distinct. In fact, I might have repetition among them. Okay, so as part of the strong induction hypothesis, I have this statement, and moreover, this field E1 is generated by alpha i's and the base field F. Okay, so that comes from the induction hypothesis. Now, next, I'm going to look at H. Notice that H itself is a polynomial with coefficients inside F, but F is a subfield of E1, so I can view this as a polynomial with coefficients inside E1. Now, degree of H is strictly less than degree of F. So again, I can use a strong induction hypothesis, but this time for the field, for the polynomial H and the field E1. So I can add zeros of H into E1 and to the field E1 and get a larger field that we call E. So by the strong induction hypothesis, this time using for the polynomial H and the field E1, we can find a field extension E of E1. There exists a field extension E of E1 and elements beta 1 dot beta k, again, there might be multiplicity among them, such that the polynomial h can be factored completely into linear factors given by x minus beta i's. I possibly need to multiply it by the leading coefficient of h, and E itself is generated by E1 and these added zeros, beta 1 beta k. So again, this comes out of the strong induction hypothesis. Now, if I combine these two together, I end up getting that the polynomial f, which is product of g and h, is product of these linear factors and this constant term b times c times these linear factors x minus alpha i's for g times the linear factors x minus beta j's for h. And the field E is generated by E1 and beta i's, but E1 itself is generated by F and alpha i's. So altogether, we get that this field is generated by F, alpha i's, and beta i's, which we denoted by this. So E is the ring generated by F, alpha i's, and beta j's. So altogether now, this proves the induction step when F is not irreducible. Now, what happens if it is irreducible? When F is irreducible, then first we are going to find a degree 1 factor by extending my base field. By the lemma that we proved, we can find some field extension that we denote again by E1 this time as well, and some element of E1 that is a zero of F, and E1 is nothing but the ring generated by F and alpha 1. This is what we proved in the previous lecture, that whenever I give you an irreducible element, we can find a field extension that's generated by F and 1 0 of this field, of this polynomial. Okay. Now, if I use the factor theorem, because alpha is 0 of F, when I use the factor theorem, I can find some polynomial with coefficients in this larger field, E1, such that F is x minus alpha, this 0 that we found, the linear factor that comes out of that 0, times this polynomial g of x. Notice that immediately we can say degree of g is 1 less than degree of f. And in particular, degree of g is strictly less than degree of f, and so I can use the strong induction hypothesis for the polynomial g. And by the strong induction hypothesis, we can deduce that I can find some field extension, E, over which I can completely factor the polynomial g. So we can find this field extension, and alpha I is inside the field extension, such that first of all, the polynomial g can be factored completely into linear factors. And when I add these zeros to the base field E1, I get the entire field E. So if I put them together, I get that f of x, which is x minus alpha times g of x, now is product of these degree 1 factors, x minus alpha 1, dot x minus alpha m, and possibly I need to multiply it by the leading coefficient of g, which is the same as the leading coefficient of f, because the other factors are monic. And E is the ring generated by E1 and alpha i's. E1 itself is the ring generated by F and alpha. So if I put them together, I get that E is the ring generated by F, alpha, alpha 1, and so on. And that completes the proof of the existence of a splitting field. Now we are going to work towards uniqueness of a splitting field. Okay, so we need to formulate it precisely. What do we mean by that? But after we prove this, it's going to play an important role in Galois theory. So pay close attention to the statement of this theorem. Try to remember what it means and so on. Actually, the uniqueness, the precise formulation of uniqueness I'm going to formulate in the next lecture, but the techniques that we are going to use here are important as well. So please pay close attention to the arguments. Okay, so again, our goal is to, among other things, show that a splitting field up to an isomorphism is unique. But we'll show a bit more than that. Similar to the proof of existence, we start with an irreducible polynomial, and we discuss what happens when we add a single zero to the base field f. So we want to show that adding a single zero to the base field f is going to give us a unique field extension. So that field extension is unique up to isomorphism. So we make it a bit more precise, and that can help us to work with two different copies of the same given field f. And we will see later why it is important. But okay, so let's formulate the lemma. So suppose f is a field, and I give you an irreducible polynomial with coefficients inside f. Now, if I happen to have a field extension E that contains a zero of this polynomial, and this field extension is generated by f and alpha, then this field extension is in fact naturally isomorphic to the one that we proposed earlier. So meaning to the quotient ring of the ring of polynomials by the ideal generated by f. So if we remember, this is how we created such a field. We said, let's consider this quotient, and let alpha be the coset represented by x, and it satisfies these properties 1 and 2. Now we are going kind of the other way around. Suppose I give you a field extension, and I tell you that alpha is a zero of this, and E is generated by f and alpha. In that case, up to isomorphism, this is exactly the copy that we have in mind, meaning there is an isomorphism between the quotient ring of f bracket x by the ideal generated by f and this field that we have, and this isomorphism is nothing but the map that's induced by evaluation map, meaning I give you the coset represented by a polynomial, and I'm going to just evaluate it at alpha. Notice that in particular, the coset that's represented by x is mapped to alpha, which is consistent with what we had earlier. Okay, so this is the lemma that we want to show next. And this is nothing but the first isomorphism theorem, but let's go through the argument carefully. We have already seen that by the first isomorphism theorem and the fact that the kernel of evaluation map is the ideal generated by the minimal polynomial, we have this isomorphism that f bracket x mod out by the ideal generated by the minimal polynomial of alpha over f is isomorphic to the ring generated by f and alpha. And the isomorphism is given by the evaluation map, meaning the coset that's represented by G is sent to evaluation of G at alpha. So when I substitute alpha for x. So this is a result that we've seen earlier. Now notice that by definition alpha is 0 of the polynomial f, and we know that if alpha is 0 of a polynomial, this happens precisely when the minimal polynomial divides f. So the minimal polynomial should divide f. But by assumption, f itself is irreducible. So this means I cannot write it as minimal polynomial times something unless one of the factors is a unit, but my minimal polynomial is never a unit, which means I end up writing f as a product of a unit and the minimal polynomial. But units of the ring of polynomials with coefficients inside the field are just non-zero constants. So altogether, we deduce that this polynomial f can be written as a non-constant, non-zero constant polynomial times the minimal polynomial of alpha over f. Because a is a unit, that implies that the ideal generated by f is equal to the ideal generated by the minimal polynomial of alpha over f. So now if I combine it with this result that we have over here, we get the claim. We get that the f bracket x modeled by the ideal generated by f is isomorphic to the field E, and the isomorphism sends the coset represented by x to alpha. Okay, so this is a uniqueness when I'm dealing with a single zero of an irreducible element. So later, what we want to do is to add zeros of irreducible factors one after another, similar to the existence part. And each time we want to say that the resulting field is going to be isomorphic to the old ones. But notice that when I add a new element, even though the fields are isomorphic, they are not the same fields. So that's why I need to work with fields that are isomorphic, but not necessarily the same thing. That brings us to the next lemma. So suppose I have an isomorphism between the fields f and f prime. So f and f primes are two fields, and I'm given a ring homomorphism between these things. So we often abbreviate these two statements and say, suppose theta is a field isomorphism. So when I say it's a field isomorphism, automatically I'm implying that both domain and codomain are fields, and this map is a ring homomorphism. Okay, now suppose f is an irreducible polynomial with coefficients inside the field capital F. In that, okay, so now what I want to do, I'm going to look at the copy of the polynomial f with coefficients inside f prime. I'm going to use theta and look at the coefficients of f inside f prime. I'm going to, you see, when I have an isomorphism between two fields, then essentially they are the same, but different decorations. So now when I give you a polynomial with coefficients inside f, I can change the decorations and think about it as a polynomial inside f prime. This change of decoration I still denote by theta. So theta of f is the polynomial with coefficients inside f prime after applying theta to each one of the coefficients of the polynomial f. Okay, so this means I have two polynomials. One of them is f, the other one is theta of f. One of them is inside f bracket x, the other one in f prime bracket x. For each one of these two, I can find some field extension, let's say E and E prime, and some elements, alpha inside E, alpha prime inside E prime, so that alpha is a zero of f, and alpha prime is a zero of theta of f. And suppose that E and E prime are smallest fields with these properties, meaning E is generated by f bracket alpha, and E prime is generated by f prime bracket alpha prime. Under these assumptions, there is a unique ring isomorphism that I'm going to denote by theta hat from E to E prime, such that when I restrict it to F, remember, E is a field extension of F, so F can be embedded into E, and E prime can be, and F prime can be embedded into E prime. You see this kind of hook shape. Whenever you see this kind of hook shape, this means that there is an injective homomorphism from from the domain to the codomain. So this hook means that this is an injective homomorphism, and you should think about it like having a copy of F inside E. This hook should remind you of the inclusion being a subset of, but because it's not quite the inclusion map, we denote it by this hook. So we have a copy of F inside E, and we have a copy of F prime inside E prime, and when we say that, so this theta hat is supposed to be an extension of this theta that we have over here. So I'm looking for this theta prime, theta hat, that's supposed to be an extension of theta, which means whenever I give you an element A over here, so if I view it as an element of E, because it's just inclusion, I can again write it as E, and then apply theta hat in order to get an element inside E prime. In order to understand what it is, I can go actually this way. I can apply theta and get an element of F prime and then embed it into E prime. So it doesn't matter which path I'm going to get to go from this bottom corner, to this top corner. So no matter what path I get, I'm going to get the same result. So whenever you have such a diagram, we say it's a commutative diagram, or this diagram commutes. This is an important terminology, and it can help us to compact, to say many conditions in a compact form, visualize many of these conditions. So altogether, what we are saying is that if E has a zero of the irreducible polynomial small f, and it is generated by this zero, and E prime has a zero of theta of f, and it's generated by this zero, then there is a unique isomorphism from E to E prime with the following properties: that first of all, the restriction to f, it should be the same as theta, and second, the zero alpha of f is supposed to be sent to the zero alpha prime. So if I know where I'm supposed to send this particular zero alpha, I'm supposed to send it, let's say, to alpha prime. And if I know what's going on, what I want to do with elements of f, then of course it's going to be unique, because E is generated by f bracket alpha. So E is generated by f and alpha. So if I know what my theta hat is supposed to do with f and what it is supposed to do with alpha, then I know uniquely what it does to all the elements of E. So the uniqueness part is not surprising at all. But let's focus on the existence part. Why do we know that E is isomorphic to E prime? Okay, so why do we have this? So the way that we can, this is exactly the commuting diagram that I discussed earlier. So essentially this diagram is going to capture the argument completely. So let's start with the diagram, and then I'll go through different parts of the diagram carefully. So again, by the lemma that we had, because f, this binomial f, is irreducible, the lemma that we had showed that whenever I take a zero of this, add it to the base field f, and get a new field, it's going to be isomorphic to this quotient ring. And this isomorphism, so if I go from the quotient ring to E, is just evaluation map. So meaning if I give you a coset that's represented by a binomial, you have to evaluate it at alpha. In particular, if I look at the inverse of this map, alpha is sent to the coset represented by X inside this quotient ring. So if you think about it, I have a copy of the field F inside E. Then this is like the coset represented by the constant binomials, and that's the copy of F inside this quotient. This was how we viewed this quotient as a field extension of F. So altogether, what I'm saying is that I'm allowed to go from this corner to this corner, and it doesn't matter what path I'm taking, either this way or either this way, going up and then to the right, or going to the right and then going up, I end up getting the same result. Okay, so that explains the first block. Now, how about the second block? Let's try to understand the second block better, and then we'll go to the third block. The first thing that we have to point out is what I said earlier, but we did not look at it carefully. Let's look at it carefully. Theta is an isomorphism between the fields f and f prime. I can naturally extend it to the ring of polynomials with coefficients inside f and coefficients inside f prime. After all, f and f prime are the same fields, and theta is the way to translate the language inside f to the language inside f prime. So when I give you a binomial with coefficients inside f, I can apply this translator, this isomorphism, to the coefficients of this binomial and end up getting a binomial with coefficients inside f prime. And it's straightforward to check that it is in fact a ring homomorphism in general, but because theta is a bijection, this map is also a bijection, and therefore this is an isomorphism between these ring of binomials. So in particular, because f is irreducible, we deduce the theta of f is also irreducible. The first one is inside f bracket x, and theta of f is inside f prime bracket x. And because theta is a bijection, multiples of f are mapped to multiples of theta of f. Because theta is a ring homomorphism, I have this equality. Okay, so now what we want to show is that the middle picture, this middle map that sends, okay, so I did not describe it here, what the map is. The map is the following: when I give you a coset that's represented by G in the first quotient, I send it to the coset that's represented by theta of G in the second coset. And it should not be surprising. After all, theta is a translator for us. So I give you G, theta translates it, and then I look at it in f prime, then I should get the same coset. And that's the isomorphism. That's the thing that we claim is an isomorphism. Okay, let's see how we can show this. We have f bracket x, which is isomorphic to f prime bracket x via theta. Then I pass to the quotient of f prime bracket x. The composite of these two ring homomorphisms, both of these ring homomorphisms are surjective. The composite gives me another surjective ring homomorphism. Now I want to use the first isomorphism theorem for this surjective ring homomorphism. Being surjective, I already know what the image is, so I need to understand what the kernel of this map is, and an element belongs to the kernel, a binomial G belongs to the kernel if and only if theta of G belongs to the ideal generated by theta of F, which is theta of the ideal generated by F. Theta is a bijection. So theta of G belongs to this theta of this set precisely when G is inside that set. Theta is a bijection, therefore we get this. So that means kernel of this map is precisely the ideal generated by F. Therefore, applying the first isomorphism theorem, we deduce that the quotient ring of F by the ideal generated by small f is isomorphic to the quotient ring of the ring of binomials with coefficients inside F prime modeled by the ideal generated by theta of F. And the map is precisely this. This coset goes to theta of the coset representative. This gives us the middle block. So we get that this middle, like you see, when I give you a coset with coefficients inside F, I have to apply theta to this coset representative, and I go from left to right. But that's the same. I mean, if I focus on the constant binomials, the cosets that are represented by constant binomials, that's exactly what theta prime does to this. So what I'm saying is that, again, the middle part is going to be a commutative diagram. Okay, so far we have two commutative or commuting diagrams, commutative diagrams. Now I focus on the last part. Notice that theta of F is an irreducible polynomial because F was, and alpha prime is a zero of this irreducible polynomial. So another application of the lemma that we had earlier implies that this quotient ring is isomorphic to the ring generated by F prime and this zero alpha prime, which is E prime. And this isomorphism sends the coset represented by X to alpha prime. So this gives us the last block and shows that the last block is also a commutative diagram. So now I'm putting these commutative diagrams together, and then I'm looking at the composite of these maps. So all together, I end up getting this isomorphism between E and E prime, which sends alpha to alpha prime, as we can see over here. And this composite commutes with this composite. But what is this composite? It's composite of identity, theta, and identity. So there is no theta prime here, sorry. This is theta. So it's a composite of these maps, which is exactly theta. This is exactly what we were looking for. We found this isomorphism between E and E prime. Its restriction to F gives us theta. So this completes the proof of this part. And in the next lecture, we are going to use this result in order to show uniqueness of a splitting field of a binomial over a field F.